Lecture 14, Synchronization Patterns. So there are a number of common synchronization patterns that occur frequently, and we can use semaphores to solve them. These synchronization patterns are just a mechanism of coordinating our threads or our processes, and actually the first two synchronization patterns we've already learned about. They are serialization and mutual exclusion. There are, of course, more, otherwise this wouldn't be a whole topic. Why are we here? And like before, this is going to mostly use pseudocode, and if you see some text that says statement A1, that's some valid statement in the program doing whatever it needs to do. The thing about the synchronization patterns is that they are common. They are something that you can use basically anywhere you need them, and when you're presented with a problem, you can think about, does this map to one of the synchronization patterns that I've already learned about? If the answer to that is yes, then you have at least an outline of a solution. So, if you know that there is some data that can't be accessed by more than one thread at a time, you can recognize that as being a mutual exclusion synchronization pattern, and you know how that is supposed to work, and you even know now how to use a semaphore, or a mutex, which we'll see in some more detail soon, exactly how to do that. And so what the program actually does isn't that important at the moment when we think about it. All that matters is we have a valid scenario where we need this synchronization pattern. And when you can see the pattern, then you can apply what you learn from this topic and the previous one, and you will again have an outline of a solution. The exact details will of course depend, and there's always the possibility of there being a new situation that you haven't encountered before or that isn't covered in this lecture, but for a lot of the ones that we are going to cover, you will find that they are common and quite relatable to problems you have already examined or will examine later. So, text me maybe. So, you will recall a little bit from earlier, we were talking about Alice and Bob being at the power plant, and that was signaling. Alice needs to send a signal to Bob to say she has arrived. Bob sends a signal to Alice to indicate he has arrived. That is a signal, and it's like sending somebody a text. So, signaling can be used in general just as a way of indicating that something has happened, or as a way of enforcing certain ordering. So consider the situation shown on the slide. We have a semaphore. The semaphore is excitingly called sem, and it has an initial value of 0. And we have thread A and we have thread B. On the left, thread A does statement A1, does post on semaphore, and thread B does wait on semaphore, followed by statement B2. Okay. So we've got a pretty simple thing worked out. There's something I do want to call some attention to, and that is the fact that I have here explicitly said what the initial value of the semaphore is, and I've said it should be initialized to 0. We have to be specific about what the initial values are. We covered that when we talked about semaphore syntax within the program, so that part shouldn't be surprising. However, in a pseudocode example, it's something that's a little easier to overlook because you don't have to declare semaphore, you don't have to call seminit or anything like that, but it's important to choose that value and to say what it is. If it doesn't appear on a slide, it is because I want you to think about what it should be and make your decision accordingly. But okay, we have a statement A1 and we have a statement B2, and signaling ensures an ordering of events here. And that is to say that we are certain, if everything is initialized correctly, that statement A1 will occur before statement B2. And this should be relatively easy to reason through. You could imagine that thread A runs first, so thread A runs statement A1, then calls post on semaphore, and then thread B runs, so waits on the semaphore. The post that already happened from thread A incremented the value to be 1. B gets to the semaphore, waits, decrements it to 0. 0 is non-negative, so thread B is able to proceed, and then executes statement B2. If it happens in the other order, thread B gets to wait the semaphore, it decrements the value, it becomes -1, and then is blocked. Thread A will continue, it does statement A1, posts on the semaphore, this unblocks thread B. Thread B can then proceed to statement B2. You can get the same thing even if there is a thread switch after statement A1. Statement A1 runs, there's a thread switch, thread B waits, gets blocked, and then we have the thread A post, which unblocks thread B, and then statement B2. So no matter what happens, no matter what order the threads run in, and no matter where in this sequence a thread switch happens, we're always certain that statement A1 will execute before statement B2. We have imposed a form of ordering in the program that says first this, then that, and we can say with certainty that there is an order, there is some serialization there, where statement A1 happens first, and statement B2 happens second, separated by some amount of time. However much is not important, but there is a defined order. Okay, so that, of course, breaks down horribly if our semaphore is initialized to the wrong value. If it's initialized to 1 instead of 0, then when thread B, if it runs first, gets to the wait semaphore statement, it proceeds immediately and statement B2 happens before A1. So it did not get we did not get the desired outcome. If we chose a value of -1, then thread B will get blocked if it runs first, but will get unblocked if it runs first, because the post from thread A will unblock it. However, it is possible that thread A runs first and posts on the semaphore, which then increments its value to 0. Then thread B runs and it decrements the value to -1 and gets blocked. So yeah, that would also not work, and thread B would then be stuck forever. So there's two observations that I want to talk about related to that. One is that, yes, if thread B ran first and the initial value of the semaphore was -1 and it was decremented to -2, then when thread A runs post, it does unblock one of the threads that's waiting. In this case, B is the only one, even though the total value of the semaphore remains negative. I've had some questions in office hours in the past that seem to be confused that this is the case, and their expectation is that you have to post many times on the semaphore and threads only start getting unblocked when the value gets to 0. So that's not the case. The semaphore is a bit asymmetric in that regard, is that if the value is positive, then threads can keep waiting without getting blocked, but when there's a post, it unblocks a thread immediately, no matter what no matter how negative the value of the semaphore is. The other thing that is worth noting is this is a scenario where it makes sense for a thread to post on a semaphore even though it didn't wait on it. In a bunch of the previous scenarios, we've done something where thread A waits on a semaphore, has a critical section, and then does post. And you could say, well, couldn't somebody do a bad thing if we don't have mutex rules that enforce only the caller of wait can call post? And here is a perfectly good scenario where that is not the case. So sometimes the semaphore is appropriate, the mutex structure is not always necessary. So yep, this slide just recaps some of our analysis, that if B gets the wait statement first, or A gets the wait statement first, we end up where we should be no matter what. Rendezvous is the next pattern that I'd like to talk about, and the rendezvous pattern is kind of an expansion of the signaling pattern so that it works both ways, that we want our threads to meet up. This artist rendering of the NASA Gemini spacecraft meeting in space represents rendezvous because they have to meet up at the same point at the same time. Rendezvous in a terrestrial sense is a lot easier. It's much harder with orbital mechanics to get get two spacecraft to meet up at the same point at the same time, because they have to be traveling in the same orbit at the same speed, blah, blah, blah. This is something you would know if you've ever tried to do docking in any space simulation game, which maybe you have. So the rendezvous is an expansion of the signaling pattern so that it works for both of them. So imagine that we have the situation as shown here, where we have thread A and thread B, each of which has a statement A1 and A2 and B1 and B2. And these are supposed to be arranged so that A1 is before B2 and B1 is before A2. So all the statements ending in 1 have to be finished before any of the statements ending in 2. If it helps you to imagine it, you could think of the steps being like prepare and then execute, and we can't start executing until everything has been prepared, so we need all the preparations to be finished before we go on to any of the executions. Okay, so 2 semaphores will be needed to make this happen. One to indicate that A has reached the rendezvous point, and one for B, indicating that B has reached the rendezvous point as well. And so we will create our semaphores, and we will initialize both of them to 0. Again, if you choose the wrong value, you do not get the correct behavior. So here's our solution. Solution 1. Thread A waits for B to arrive after it's completed statement A1, posts A arrived, and then we have statement A2. And thread B, statement B1 is followed by wait for A to arrive, then post on B arrived, and then we have statement B2. Okay. Again, I remind you that both A arrived and B arrived are initialized to 0. So does this work? Again, I give you the opportunity to look at it for a minute and think about it, and let me know what you think, even if it's just to yourself. But you should try to think about it and identify, is this correct? All right, our answer is no, and hopefully you spotted the problem in this, which is that thread A gets to the wait statement, and it waits until B posts its arrival before it can proceed, and thread B gets to the wait statement and waits for A to post before it can proceed, and each of those threads is then waiting for the other, and neither of them can get to the actual post statement because they are both blocked. And you can see that scenario if thread A runs first, does statement A1, waits for B to arrive, is blocked. Thread B waits for does statement B1, waits for A arrived, is blocked. They're both blocked. Nobody can get any farther, and they are permanently stuck. Now, one of the things that's nice about our sort of investigation of does the solution work is there could be many paths that are bad. There could be many ways in which the solution does not work. In this case, it is they get stuck if the order of statements is A1, then A2, then B1, then B2. There could exist lots of other possibilities like B1, then B2, followed by A1, then A2, or you could have switching back and forth between the threads. Doesn't matter. If you find one scenario where a bad thing happens and we do not get the correct behavior, in this case, both of the threads get stuck and nobody is able to proceed, that's enough. You can say this solution is garbage, we cannot use it. So if I ask you to say what's wrong with this, you don't have to enumerate every possibility of what's wrong, only one would eliminate it as being no good. This, of course, makes it a lot harder to prove that something is correct. If something is correct, you have to try lots of scenarios to convince yourself that it is correct. If something is wrong, you only have to try the one scenario that you know is going to fail. So, yeah, neither thread can proceed, and this situation can actually never be resolved because there's no other force that would cause one or the other thread to be unblocked. The situation shown is a deadlock. Deadlock is a subject that will get its own discussion in the course a little bit later on. But for now, we will just take an informal definition, and that is all the threads are permanently stuck. The permanently in that sentence is an important word because you can have a situation where all threads are stuck, they're all waiting for something, they're all blocked, but there is a hardware interrupt that will happen, say when a disk read is complete, that unblocks a thread. That is not a deadlock because even though all threads are blocked right now, they will be unblocked. It's not permanent. Only if it's permanent do we actually consider it to be a deadlock. Obviously, deadlock is undesirable. We will not want that to happen. We would like to avoid it if we at all can. And we would, generally speaking, if we can't avoid it, deal with it. But that is a subject we will return to in a few lectures. Okay, so what if instead the threads reverse their statements of wait and post, and so they post first before they wait. So thread A does statement A1, then post its arrival, then wait for B to arrive, then we have statement A2, and thread B, again, is analogous, statement B1, then post B arrived, then wait A arrived. How about that? Does this fix the problem, improve the situation? Okay, the answer to that is yes. This does work. If A gets to the rendezvous location first, it indicates its arrival and waits for B. If B gets there first, it posts its arrival and waits for A. Whoever gets there last will post and unblock the other before it calls wait, and whatever thread gets there second will not be blocked when it calls wait because the post from the other thread has likely already happened, and we're okay. Again, to actually demonstrate that it works, you would have to try a lot of different possibilities to prove conclusively that it is never going to cause a deadlock. That could be somewhat complicated, but it's possible. We don't have too many lines, and there aren't too many orders of execution that need to be considered. Now, maybe when you look at this solution, something comes to your mind that it's actually not a minimal change set. What if instead we changed only one of the threads? I'll choose B, but you could imagine changing A as well instead. It would be equivalent. Does this accomplish the same goal? Does it allow this code to work without a deadlock occurring? Again, to convince a reader of your solution, if you were writing it on a quiz or exam or something like that, you may have to try many different possibilities because making an argument that is based on, well, if this, then that, is not necessarily as easy to say, like, here's the order of statements, and they all work. Okay, this one does work as well. But it doesn't work as efficiently as the other one. It does potentially require an extra switch between processes because there is some possibility of a workflow where statement A1 happens, then we get blocked, then we switch over to B, then we post, then we go back to A because we get blocked here at this thread B's statement 3, and then we post on A arrive, which unblocks thread B, and then they can both continue. There might be a little bit of extra back and forth depending on just the order in which these happen and when your thread switches occur. Okay. as long as you're sure that deadlock doesn't occur, or, and I should say, as long as you're sure that deadlock doesn't occur and the objective is achieved, so it does provide the rendezvous behavior that we're looking for, then in this course, I consider a solution to be acceptable. It does not have to be an optimal solution, it just has to be a correct solution, and that is okay. In the future, if you take programming for performance, then I might hassle you about an inefficient route where we have potential extra switches that could be avoided. However, for now, you don't have to supply the optimal solution, you just have to supply a correct solution, and that will be just fine. Suppose, however, I asked you if you wanted to add a third thread to this rendezvous. What would you have to change? And while you think about it, I'll put back on the screen the solution 2, the one we said was the best solution that we looked at so far. Obviously we have to create a thread 3, and it will have statement C1 and it will have statement C2. But what else would we have to change to make this happen, and what would the implementation of thread C look like? Okay, so in designing your solution, no doubt you recognize that statement C1 should appear at the top and statement C2 should appear at the end of thread C. And thread A should now be waiting for its colleagues B and C. Thread B should be waiting for A and C, and thread C should be waiting for A and B. So knowing all those things, it shouldn't be too hard to produce some code for that. So let's add C to the party. Thread A has statement A1, posts its arrival, waits for B, waits for C, and then can go on to statement A2. Thread B has statement B1, posts its arrival, waits for A, waits for C, then has statement B2. Thread C has statement C1, posts its arrival, waits for A, waits for B, and then goes on to statement C2. Is this correct? Well, the answer to this one is no. This will also lead to a deadlock. A call like post A arrived unblocks one of the threads that is waiting for A, but now there's 2 threads that are waiting for it. So when we have your statement A1, for example, it calls post A arrived, and then wait on B arrived, thread A gets blocked. Thread B will execute statement B1, post on B arrived, wait for A arrived, semaphores, if they're initialized correctly to 0, then thread B will proceed and it will get blocked here, waiting for C arrived. Thread C can run statement statement C1, post C arrived, wait for A arrived, and this thread will get blocked here at this point. At present, the only thread that's able to proceed is B, because it waited for C to arrive and gets unblocked, so it does statement B2. And thread B escapes from this deadlock, but A and C are stuck forever. If you choose a different order, you can end up with different threads that get stuck. It is entirely possible to get many threads stuck. It doesn't just have to be 2 of them. You could have more than 2 that get stuck. However, our solution is not sufficient. It's not enough for just B to get through this alive. All of the threads have to complete the rendezvous correctly, so the solution does not work. What's wrong? Well, there's not enough post statements, basically. Statement A1 is going to happen, and then post A arrived happens only once, even though 2 threads, B and C, are waiting for that post. So we need to, well, do it more. And this is actually one of the analysis tools that I want to recommend. When you are looking at a solution, you should look at the number of wait and post statements. And part of your argument for does a solution work or not could revolve around whether or not this number is in balance. That is, if there are many more wait statements than there are post statements, that's concerning because it probably means that there aren't enough post statements and we might have a deadlock, as we have here. If there are a lot more post statements than wait statements, it suggests that the value of the semaphore is being incremented a lot, and so threads might not be waiting when they should be waiting. We can consider the number of wait and post statements to make sure that they are in balance, and if they're in balance, it's a good sign. Obviously, in the first example that we did, signaling, where it was just wait from one thread and post in another, that is balanced. That's good. We like that. In mutual exclusion, if you have a wait at the beginning of your critical section and a post at the end, again, balanced. And even in the Rendezvous Solution 2, the one that worked with just A and B, we had one wait on each semaphore and one post on each semaphore, and that's good. But here in our rendezvous of 3 threads, then we're not in balance because we have 2 waits on each semaphore, but only 1 post. Okay, so do we successfully fix that by doubling up on the post statements? The answer is yes, and one of the signs that this is correct is that our wait and post statements are balanced, but also, again, to demonstrate that it works as expected, you would have to go through all of the potential workflows for where does a thread switch occur and demonstrate that there is no such possibility where different threads all get stuck. Okay. This kind of solution isn't great. You can imagine that the complexity increases if there are more threads. That if you have a thread D that you wanted to add to this, then not only do you have to write the code for thread D, but you have to go back and change A, B, and C, and then you have to change A, so there's 3 post statements and another wait statement here, and change B, so there's a 3rd post statement here and another wait statement, and same for C, and this becomes sort of exponentially, well, not exponentially, but linearly bad with the more threads you have, and if you wanted to have 12 threads or something, you will be saying, like, why do I have to write so many wait and post statements? So we would like, I think, to get away from that kind of solution. We would prefer a solution where when we want to add something, it doesn't require us to go back and change everything. This, as you might imagine, is also just sort of generally valuable in software engineering, that if you can make your changes without unnecessary or redundant changes to other parts of the program, it does make it easier to actually implement a change. So we're going to examine that, but in the context of mutual exclusion. So mutual exclusion, wait your turn, is something I think we're all a little bit familiar with, and we've all waited in a line of some sort or a queue in some case. Of course, the people shown in this picture are not social distancing, so this is a sign of when this picture was taken, I suppose, but they should be social distancing. Now, we saw already motivation and examples of mutual exclusion, and the general form of that in your pseudocode is wait on mutex. You can name the semaphore mutex if you want, same thing. But it does have to be initialized to 1, unlike the previous examples where we started at 0. As before, if we chose the wrong initial value, then we don't get the right behavior. If we started at 0, neither thread would ever be able to enter into the critical section, and that would not be okay. Similarly, if we chose a different value, 20, then both threads would go into the critical section at the same time, and that's not what we want. So whoever thread gets to run first, they get to the wait statement, proceed immediately, not get blocked at all. Now, A and B are identical in their code. There's no difference between their statements, and that is what we call a symmetric solution, because every thread has the same synchronization behavior, does the same wait and post sequence in the same order and all that, which is helpful because it makes it a lot easier to predict what's going to happen when threads are going to do the same thing. The previous example with the rendezvous was an asymmetric solution because every thread had different code, and you can imagine if I was creating a thread D and I needed to add all the wait and post statements, it's possible to make a copy-paste error and would not necessarily be noticed immediately, but would lead to a deadlock at runtime. Symmetric solutions are good because they scale pretty well. You can have arbitrarily many threads executing the same pattern as long as they all do the correct things. They wait when they are supposed to wait and post when they are supposed to post. Then nothing really goes wrong, and we're certain that mutual exclusion is enforced. Now, along the lines of mutual exclusion, I want to expand on that a little bit. I've talked about critical section as though there's only one, but there can of course be multiple critical sections in the program. But I've said when we talk about a critical section that there should only be one thread in a critical section at the same time. And sometimes actually we're going to relax that constraint using the general semaphore, and that is you can intentionally make a decision about initializing a semaphore to some value n, allowing n threads to be in a critical section at the same time. Panic and freak out, I know, like, what do you mean multiples in the critical section at the same time? It depends what's in your critical section. Obviously, if you're manipulating variables that are shared, you can't have multiple threads in the critical section at the same time. But sometimes your critical section is something that you want to have only a certain amount in progress at the same time. So an analogy for this is a restaurant. When restaurants are open and you can sit in them, they have a certain number of tables and seats, and if more people want to eat at that restaurant than there are seats available, then those customers have to wait until some seats become available, which is basically when other customers leave. And restaurants generally want to pack in as many seats as possible. They would love to have more customers, but fire safety regulations set a maximum occupancy for a given space, and therefore they have to limit how many people can be in the space at a time. So you could think of a general semaphore being used in this purpose to more or less keep track of how many people are allowed to be in the restaurant at a time. If you want a computer-related example, which maybe makes it a bit clearer and a bit more relatable as to why you might want a general semaphore, is you have a system where there is a problem when there are too many database requests at the same time. Queries become slow and eventually run up against some timeout, and then nobody can really get anything done because your query keeps failing because you requested and you have to request it again. So a potential solution is you just use a regular mutex or binary semaphore, and only one database query can run at a time. That might be too restrictive a policy. You might discover that you are wasting a lot of database resources by only allowing exactly one query at a time. You might actually find that you can always run 5 queries concurrently, no matter how complicated they are, without any slowdown. Maybe in real life you could run 50 queries concurrently, or maybe it depends on how complex your queries are, but for the sake of the example, we'll choose 5. So what you could do then is initialize your semaphore with a value of 5, and then treat it as if it is regular mutual exclusion, and that allows a maximum of 5 threads into the critical section at any given time, when each thread that's in the critical section then can actually invoke a database request. So yeah, the general semaphore can be used for this. It's not just for mutual exclusion scenarios where only one thread can do a thing at a time, even though that's usually how we think about it. Now, to show you the pseudocode for the multiplex is it's just this. It is exactly the same as the regular mutual exclusion, and it works for arbitrarily many threads because it is a symmetric solution, as expected. The only difference is what is the value of mutex, and this is another illustration of what I mean about the importance of choosing the correct value. It's not always just 1 or 0. Sometimes 5 is correct, sometimes 50 is correct. It is just design decision for your system, and if you want to allow this many concurrent things at a time, that's what you choose for your initial value of the semaphore. Okay, so I hope you were thinking in the meantime about what to do about a symmetric solution for the barrier problem. And if you like, maybe take a few seconds to consider how would you make that solution symmetric. The barrier problem is the same as the rendezvous problem, I should say. I don't think I mentioned that before, which is that we need all of these threads to meet up to get to this same point, and so a rendezvous is, well, just like a barrier. In this case, is that they all have to complete phase 1 before any of them are allowed to go on to phase 2. And yeah, how would we generalize this? This one is not that easy. There is there's a certain amount of uncertainty, I think, because what do we need to make this happen? A general semaphore wouldn't do the trick, because you can't set the value of the semaphore to be -3 in the expectation that, well, we can just wait for 3 threads to arrive and then they start getting unblocked. I covered that a little bit earlier, so that won't work. But it would be an interesting idea if semaphores actually worked that way, but they don't. So what ideas do we have? All right, the first hint that I will give you is that some problems require combining more than one semaphore, so maybe it will help you to think about how to solve this problem if we have more than one. Another thing that will help is that we do have to know how many threads intend to rendezvous, how many will be at the barrier, like with an actual integer number. Yeah, this is not an easy one. So, given n threads, each of which knows that the total number of threads is n, the behavior that we're looking for is that when the first n-1 threads arrive, they should wait until the last one gets there. And as a solution, you could keep track of the number of threads that have arrived at a given point. This is going to be shared data. If they're going to each increment this count saying, oh, I have arrived, then we have to put that in a critical section. If you wanted an analogy for this as well, again, sort of going back to the restaurant approach, sometimes if you go to a restaurant, you are a group of 5 people, but they won't give you a table until everybody from your group has arrived. So the first n-1, so 4 people arrive at the restaurant and they have to wait in the waiting area for the last person, and there's always the last person, and it's entirely possible in your friend group it is consistently the same person who, for whatever reasons, lives basically in their own time zone, set back 10 or 20 minutes from the time zone that the rest of us live in. We all have a friend like that. It's not bad. You just plan accordingly. But we want to keep track of how many people have arrived so far. That's a variable, it's shared data, and modification of it should be in a critical section. So we're going to have a semaphore initialized to 1 called mutex, which will be used to keep track of, which will be used to protect this counter. And we will have another semaphore called barrier. That's the place where threads wait until the last one arrives. So this is the host who is unfriendly at this restaurant, saying everybody has to wait until the last person arrives. So given those things, how do we compose a solution? Right? The behavior of each thread is it should increment its count So we should increment the shared count. So saying yes, so I am thread number 3, and I have arrived. And also we should indicate when we are the last one. If we know that, then indicate that and post on this barrier, which will unblock people who are waiting. Okay, so here is our first draft solution. We will wait on the mutex, increment count. If count is equal to n, post on the barrier, and then end if, and then wait on barrier. So if I am the very first thread to arrive, count is at 0, so I will wait on the mutex, increment count to be 1, post on the mutex, check, count is not equal to n, so I will skip over that section and then wait at the barrier. If I am the last thread, let's say there are 10 in the example, I will wait on the mutex, increment count, count is 10, post on the mutex, if count is 10, yes it is, post on the barrier, and then proceed to wait on the barrier. All right. Does this work? All right, we already have the analysis tools that we need to know that this is a problem, and it is the balance of wait and post statements. Wait and post on mutex is balanced. Every thread does wait on mutex, and every thread does post on mutex. That's no big deal. However, our wait and post statements for barrier are not balanced. Every thread unconditionally does the one on statement 7, wait on barrier, but only if count is equal to n does post on barrier happen. So we have, if there are 10 threads, 10 waits, but only 1 post. So that's not good. It will allow a thread to be unblocked, whoever is lucky enough to be unblocked when the call to post happens, but that thread and that thread only is allowed to proceed. All the other threads, in my example, 9 of them, are stuck waiting for a post that never comes, and we have a deadlock, which we do not like. Now, you might have an idea about what to do about this. The Oprah approach. You get a signal, everyone gets a signal. So, yeah, the last thread should post a whole bunch of times. So wait on mutex, increment count, post on mutex. If count is n, if we're the last one, then do this from 1 to n. Post on the barrier, and then exit the for loop, exit the if statement, and then wait on the barrier. All right, did that help? Did that help? The answer to this is, well, yes, our wait and post statements are now balanced. I wouldn't say we're finished with this solution yet, but our wait and post statements are balanced. So we have enough waits and enough posts. Nothing to complain about there. There is a potential efficiency improvement that we could make to this. This allows all the threads to proceed, but whichever thread gets there last is probably the lowest priority thread. Please don't extrapolate that to be about the friend who always shows up late. That's unrelated. But when the last thread gets there, it posts on the semaphore, and it's likely, because this is the lowest priority thread, that whichever thread just got unblocked is going to be the one that runs, meaning we have about twice as many process or thread switches as are the minimal necessary amount. So yeah, ideally we could skip that. We could save ourselves from some of that trouble by not having quite as many process switches. In fact, we could do it with n in the best case scenario. And the way to do that would be to change it so that it's not the case that the last thread sends post to everybody, but instead that the thread that gets unblocked as its next action unblocks another thread. And that's what happens here on statements 7 and 8, which is the last thread to arrive unblocks somebody who's waiting at statement 7, and whenever a thread passes through this barrier here, and the first thing it does is unblock the next one, thus allowing the next one to execute. This pattern that we see here of wait followed immediately by a post is a common pattern that's referred to as a turnstile. Turnstile should be somewhat familiar to someone who's traveled by subway in Toronto or, as in this picture, in New York City. A turnstile allows one person at a time to go through, and when person has proceeded through, the next person can proceed immediately, although in the case of a subway system like this, you have to tap your card or swipe your card or what have you to pay for your ride. But turnstile pattern allows one thread at a time to proceed, but turnstile comes with a nice feature that allows the turnstile to be locked to bar all of the threads from proceeding, and that is the case on our previous example. The barrier here as our turnstile starts out being 0 if we initialize it correctly, meaning that no one is able to proceed until the last thread arrives and unlocks it with the post here that's within the if statement on statement 5. And that's actually represented a little bit on your typical subway terminal here as well, that you can lock the turnstile and it doesn't allow anybody to pass, and someone would have to unlock it before that could continue. So yeah, we do want usually a turnstile to initially be locked, otherwise we don't get the correct behavior that we would otherwise be expecting. But once it's unlocked, it permits all of the threads to go through. Okay, so alert readers or viewers have been probably screaming at me for quite a while now, through their computer screens or writing angry things in the comments. I can't believe he missed this. 0 out of 10 would not recommend, hitting that dislike button. I don't know. One of the things that was wrong in the previous solution was that we were reading the value of count, a shared variable, without the protection of a semaphore. And if I go back and I show you, you'll see what I mean. That here on statement 4, if count is equals n, this is a shared variable and is being read outside of this wait and post critical section. Is this dangerous? Yes. However, there is an alternative that's worse. And I say in this specific instance worse because under normal circumstances we shouldn't have the read of this shared variable outside of a critical section, otherwise we could read the wrong value. However, this does not solve the problem. Consider this instead. So we do a wait here on mutex, increment count, if count is n, post on the barrier, then wait on the barrier, post, and post on mutex. The first thread that comes along will wait on the mutex and get skip over the if block and get blocked here at statement 6. Everybody is then, like any further thread, is going to get stuck on statement 1 at wait mutex, because the first thread has not posted on mutex and nobody can ever get to a post barrier statement, and everybody is stuck forever. So that's a problem. That isn't a good solution. We haven't fixed the issue. We can, of course, fix the issue. We'll see in just a bit how to deal with that, but this isn't a correct fix for the problem. In this case, we are, for now, just going to live with reading count the wrong way, but we will fix it very soon before we consider our solution finished. However, this does highlight a very common pattern, and so I present you this solution mostly because I want you to spot this pattern, which is one of the ways that we could get deadlocked is that we are waiting on a semaphore while we are holding on to one. Now, when I say holding on to one, that is one of the terminology phrases where we say we've acquired a lock or we've acquired a semaphore or something. When we wait on it and we do not get blocked, we have successfully entered the critical section. We might say that this thread is holding a lock or holding a semaphore or something like that, or has acquired it. And so here on statement 1, we have a wait statement where we have locked this mutex, or we have decremented it, we've entered the critical section. And then on statement 6, we have another wait, and we have nested waits. So whenever you see a nested wait, that should be concerning. That should be something that tells you, like, oh, I need to check carefully to make sure that a deadlock can't happen, because it's one of the many ways in which a deadlock could occur, is that when there is a nested wait, then if we get blocked on the second one, the inside one, then we might be stuck forever. So this should be a danger sign to watch out for. Okay. So yeah, our counter in the previous example where we unlock mutex way at the end, counter can never get past 1, the condition of count equaling n is never true, and all of the threads are stuck. The barrier solution that we have is okay. We can make it better, but it's a start. But one of the things that we want to do is make it reusable. So once the barrier is opened, it can never be closed again. So we effectively have a one-time use thing. Once count gets to n, that's it. The barrier is opened. It can never be closed again. And programs frequently want to do the same thing over and over again. So one-time use barrier is not ideal. You can, if you want, and there's lots of code that does this, you create the barrier and it's a single use, and when it's done you dispose of it, but then you need to create another one in the future when you want to have barrier behavior again. That might be inefficient, with deallocating and allocating the memory and all that. You might prefer to just allocate it once and be able to reuse it. So let's do that. One of the things actually that tells us that the barrier, as we've seen thus far, is not reusable is that our wait and post statements are actually not in balance. If I go back to the barrier situation where we don't immediately deadlock with the turnstile, we actually have one extra post here, because if there are 10 threads, 10 of them wait at barrier, 10 of them post, and there's an 11th post here on line 5. So this isn't actually reusable because the final state is not the same as the initial state. If we could change it so the final state was the initial state, then we don't have to deallocate and reallocate everything, and that might actually save some time and save some effort. Okay, so yeah, let's try that. So wait on the mutex as before, increment the count, post all that stuff up to statement 8 hasn't changed from our last example, which we said isn't horribly wrong. Then we have, just I put in square brackets, critical point. Think of it as the critical section. It's the area that everybody was waiting for in the barrier section, and now they can proceed to it. So in the restaurant analogy, the first part is that everybody arrives at the restaurant, and then critical point is people sit down at the table and eat, and then afterwards, then people leave. And so again, there's wait on mutex, decrement count, post on mutex. If count is equal to 0, then wait on the turnstile, which locks the turnstile behind us and says, yeah, put it back into its initial state. And we can see, of course, that we have a reusable barrier for one reason, because we have a balanced number of wait and post statements. So mutex, again, is straightforward. Every thread does wait and post on mutex, so there's no concern for balance there. And every thread does wait and post at lines 7 and 8. And as before, there's one extra post on line 5, but it's balanced now by an extra wait at line 14. So our total number of wait and post statements is pretty good. That's it's balanced. It means that if turnstile is initialized to 0, when all of the threads have run through, the final value for turnstile will be 0. So that's pretty good. Still, I haven't addressed the problem with reading of count outside of the critical sections. Now there's 2 of them, both here at line 4 and then again at line 13. And if you wanted to see the problem with that, just imagine that thread n-1 is about to execute line 4, and there's a process switch, and the nth thread comes to this point. When they both continue, they both post on the turnstile. So thread n-1 gets here, increments count, so count is now 9, posts on the mutex, and then there's a thread switch. Thread 10 gets here, increments count, count is 10, posts on the mutex, count is 10, does post on turnstile here at line 5. When thread 9 gets unblocked, it checks here and sees, oh, count is 10. So I'm going to post on turnstile, and we had an extra post there that was not good. An extra post in this case doesn't mean that any threads get deadlocked, however. It just means that the barrier is not reusable because the final state would not be the same as the initial state, because through a run like that we would end up with a final value of the semaphore of 1 instead of 0, so it isn't reusable. The same kind of problem could occur at line 13, where if the second last thread does post on mutex on line 12, and then there's a thread switch, then 2 threads could call wait on turnstile at the end. That would actually be a bigger problem, because a thread could get blocked if they were the second one to do wait at line 14, and we're not okay with that, so we need to fix that. Okay. So wait on the mutex is still the same. Count is incremented, and now the if count is equal to n, post on turnstile happens within this critical section, and post on mutex now happens at line 6. Okay, down below we wait on mutex at statement 10, decrement count. If count is 0, wait on the turnstile, and then end if, and post on the mutex is the last thing. Alarm bells should be ringing when you look at this. What's got you worried? Yeah, it should be lightly concerning to you that there are nested waits. In particular, the wait at line 10 and wait at line 13. Those are nested. The wait at line 13 happens inside of the wait of mutex. So, you should be thinking, is there a possibility for a deadlock to occur here? How would you reason about that? Well, one of the ways is to work backwards. So you imagine, okay, if I assume that a deadlock has occurred, that means that a thread got blocked at the statement of wait turnstile. Okay, what does it take for a thread to get blocked at that statement? Well, for that to happen, the value of turnstile after the decrement has to be negative. So turnstile has to be 0, or a lower number than 0, but just go with 0 because it's the easiest to achieve, at the time when that happens. Okay, can that scenario happen? Can turnstile be 0 at the time when statement 13 is executed? Try to think about the value changes for turnstile to make that happen. I've, at this point, used hard number of 10 for the number of threads, but obviously your solution should work whether there are n threads, arbitrarily many. So could we ever get turnstile to be 0 at statement 13? Well, one of the ways that you can try to figure out what could the value be is we start from our initial value, and we make a determination about how many increments and decrements there are of the semaphore. So what do we know so far? Well, at line 7 and 8, we have wait and post, and those happen n times for each thread, so there are n waits and n posts. Okay, so far in balance. There is an additional post at line 4. That one will happen once and only once. We should be able to convince ourselves of that because count is incremented inside the critical section, so only one thread does it at a time, and therefore it only happens once. And so we have one more post than we have wait, meaning that the value of turnstile will be 1 by the time we get to the wait at the mutex here for statement 10. And therefore, it can't be 0, and it means that only one thread that does wait at turnstile on statement 13 will run, and it won't get blocked because it has a value of 1, and the value returns to 0. So we can argue, and you could choose to argue it, counting, there are n weights plus 1, and there are n posts plus 1. You could do that. You could also sort of think of it as more of a ledger, that like every weight is a decrement and every post is an increment. So you could say, well, lines 7 and 8 cancel each other out because it's minus n and plus n, and then all you have to do is prove that you get to 0. Either way, doesn't really matter. Whatever mathematical scorekeeping you want to use, if our weight and post statements are correctly balanced, there's no possibility that we have statement 13 being one where somebody gets stuck. So that's pretty good. We can take this. It is a viable solution. Yeah. There is one more problem with the reusable barrier, and I mean, it's perfectly fine as it is, but there's one more thing that could happen. And it is, what if a thread, we'll say it's thread 2, gets through the second mutex and it's running in a loop and it goes back through the first mutex again. So we don't necessarily get exactly the correct behavior because not all of the threads do what they are supposed to do. Imagine, if you will, that you have a again, the restaurant analogy. There's 5 people who want to show up for the restaurant, and after everybody sits down, they have lunch, and one person is very quick at paying and leaving, and then they pay, they leave, and then they come back to the restaurant, and they want to sit down at the table again, and they join you again for second lunch, because in this example everyone is a hobbit, I guess. And then like one person is one lap ahead of the others. Everybody's still eating their first meal, and this person is eating their second. We could prevent that by having 2 turnstiles. That is, all the threads wait at the first turnstile until the last one gets there and then lets them through. And then there's a second turnstile, so until the last person is done, and then everybody lets them all through again. This is more akin to the idea of if you want to go to a restaurant and you have to wait for your whole party to be there, then you have a turnstile that says, this is the host, that says we have to wait for everybody to be here, and then you can have a table. And then the second stage is maybe nobody is allowed to leave until everybody has paid. Something like that is perhaps a way of thinking about it. Another way you could think about it is a 2-stage pedestrian crossing, and that's actually the illustration that's shown here. If you want to cross a boulevard of sufficient size, pretend it's University Avenue in Toronto, where there's a couple of lanes, and then there's a pretty big island in the middle, and then there's a couple of more lanes, you have a 2-stage pedestrian crossing, and each stage has its own signals. And because it's pretty big, there's no expectation that you're going to travel from one side of the street to the other in one shot. You will do the first part, then wait, then do the second part. So this is a 2-phase barrier. So in the first part, the first turnstile is closed and the second one is open, hence the second one being represented by a walk symbol and the first one being represented by a don't walk symbol, with a little artistic license taken on shading them in and colors. So all of the threads will gather at the first barrier. That's the first image in the diagram from left to right. The second image shows the last thread arriving. When the last thread arrives, it unlocks the first turnstile and locks the second one. And you'll notice in the third diagram the symbols have changed. So the first barrier is now unlocked and the second one is locked. Then all of the threads proceed to the second stage, so they do whatever it is they were supposed to do, eat, critical point, whatever it is. And they are gathering there until the last thread, which could of course be a different one, arrives here in the second waiting area. And when that happens, the last thread switches the signals again, so lock the first barrier behind it and unlock the second one in front, and then all of the threads are allowed to leave. And what this addresses is the problem of, for example, if we didn't lock the second barrier, when we look at the fourth diagram in the middle, if that second barrier did not exist, then a thread could leave and go around and re-enter while the turnstile is still open. So yeah, we wouldn't want that. And so to actually make this work, the pseudocode for the reusable barrier solution looks like this, in that it resembles to a great extent the reusable barrier that we've talked about, just now there's 2 of them instead of 1. So wait on the mutex, increment count. If count is n, if we're the last thread to arrive, then we lock the second turnstile and unlock the first one. Otherwise, just skip that if block, post on the mutex, wait at the first turnstile, post on the turnstile when we proceed through. We have our critical point. When we are leaving, decrement count. If we are the last one, then we lock the first turnstile, we unlock the second one, otherwise skip the if block, and then post on the mutex, and then wait at the second turnstile and post on the second turnstile. So this is our 2-phase barrier. If we are the first thread that's arriving, we'll wait on the mutex, increment count is 1, skip the if because it's not true, post on the mutex, wait at turnstile 1 and get blocked. If we are the last thread in this phase, then we do the locking of the second turnstile and the unlocking of the first. And then we can proceed because we've unblocked the next thread, which unblocks a thread after it using the post statement. And so all of them proceed through the rendezvous. And they proceed through the critical point, and then gather up here in the lower part, and in the second waiting area, before they are allowed to leave by whoever gets there last. So yeah, the visual diagram, again, maybe makes a little bit more sense in that we wait for all of the threads to arrive at the first part. Once they're all there, they can proceed, and when they're finished, they go in a waiting area, but they can't leave the waiting area until everyone is in the second waiting area, at which point they are allowed to leave. And at that point, if they loop around and go back into the first waiting area, nothing bad happens. Nobody sneaks through, nobody's having a second meal while everybody is still eating their first. So everybody is at the same phase of completion. There are scenarios, of course, where it doesn't matter how many meals any individual person has, as long as all of the food gets eaten. If there is some work to be done where it doesn't matter very much, then probably don't choose this barrier pattern. However, in a lot of scenarios, you do want to make sure that all of the workers, all of the threads are on the same page or at the same stage of completion, and that's what this is for. Okay, so we've covered a number of synchronization problems. Like I said, this is not all of them, and when we pick up again in the next video, we're going to talk about a particular class of problem called the producer-consumer problem. And I know I've introduced that subject a little bit more, but we will have much more time for a deep dive into it because it's one of the most important problems and can represent a lot of systems. Nevertheless, I think that given what we know from this topic of synchronization patterns, when you encounter one of them, in the wild, whether a personal project or in the workplace or even in an assignment, it will give you some idea about how to handle it. You can just look at the pseudocode in this lecture, and you can say, aha, I now know how to apply this, and just implement it using code. So yeah, we will stop this one here and pick up again next time in that next video where we're going to look at the producer-consumer problem.